So this is roughly the plan for the next 4 lectures, which are supposed to be covered by me, including today's one. So today we are going to mostly be talking about the classical Maxwell theory, discuss what is the gauge invariance, what is the action, and why is the action the way it is. The next lecture, which is next Friday, we are going to start discussing quantizing the Maxwell theory using path integral, which I take it you have already seen in context of scalars and fermions. The next lecture, we are going to discuss coupling to charge matter, and specifically we will focus on QED. And if time permits, we might discuss a few other cases, but our primary focus would be QED. We will discuss how to derive the Feynman rules. And on the final lecture, we are going to focus entirely on evaluating the S matrix, the scattering cross sections at tree level for various interesting processes in QED. Okay, that's the rough idea. A brief word about the notations. The Greek letters are always going to be Lorentz indices, which runs over 0, 1, 2, 3. Lowercase English alphabets will be the purely spatial indices, which will run over 1, 2, 3. And the metric, I will use the mostly minus signs. And I think I will always set the speed of light and the flux reduced constant to 1. Okay. So with that, let us begin with the first lecture. And the first task at hand is that we want to build an action functional. So any field theory starts with this, that we have to build an action functional. And the question is that how to build the action. By now, all of you are expert on this. So the first step is to identify the correct field variables that will capture the degrees of freedom of our theory. The next step would be to identify all possible symmetries that we expect our theory to have. And finally, because we already know that the correct potential dynamics has to be given by the set of equations which are our familiar Maxwell's equations, so our action must reproduce the Maxwell's equations as the Euler-Lagrange equations. Okay, these are the standard procedure that you follow for any field theoretic construction, which is the same thing that we are going to follow for Maxwell's theory as well. Now, I hope that all of you have seen Maxwell's theory or Maxwell's equations in some form or the other. So let me just, for a brief 5 minutes, let's write in the form where everyone has seen, at least in this form, I assume. So we have divergence of E, which is rho, which is curl of B minus del T of E is the current density J. Divergence of B is 0. And finally, we have curl of E plus del T of E to be 0. Okay? So these are the Maxwell's equation. Do I need to say anything else?
No, thanks.
Okay, so someone is saying no. Do I have any other answer from the audience, or is this all? Like if I say this thing, this is the Maxwell's equations, I have perfectly described the Maxwell's equation. Do I have any other different answer from the audience?
All units are one. Permittivity, epsilon.
Absolutely, because I said C equals to 1, right?
Yeah.
So so I'm definitely not going to have any permittivity or permeability. So constants are not the issue. I'm talking more about the mathematical justification. So there is one thing that I need to say. So this rho and j cannot be completely arbitrary, right? Because I have to ensure that they satisfy the continuity equation. That's for self-consistency. Because I can take a del t here, and I can take a divergence here. The divergence kills off the curl term. Then I have divergence of del t here and del t of divergence, which commutes. So if I add these two will cancel. So del t of rho plus divergence of j has to sum to 0. So rho and j cannot be completely arbitrary. They have to satisfy the continuity equation. Okay. So once I say this information, that specifies the Maxwell's equations in a self-contained manner. If I don't say this last thing, that's not completely consistent. Okay.
Yes, got it.
Thanks. So this, as you know, are called the inhomogeneous Maxwell's equations because the right-hand side is not 0. And these are the ones which are usually called the homogeneous Maxwell's equations. Okay. And then let's discuss that how to go through the steps that I outlined upstairs. So first step is to identify the correct field variables. So what are the candidate field variables for Maxwell's theory? So
নাই নেকি বজাৰত
sorry.
আজি নাই মানে ঠিক আছে উপায় নাই ঠিক আছে
Okay, I think someone has microphone on, but probably not a question. So what's the correct field variables? The standard guess, it could be the electric field and the magnetic field. Some of you might also guess that whether it could be the potentials, the scalar and the vector potentials. So, or could it be, simultaneously both, something else? So we'll have to discuss that. That's one possibility. About the symmetries, of course, we expect a Lorentz symmetry because of relativity and of course translational invariance, because every field theory has that. But then the question is that, is there anything else that we need to worry about? Or is it enough? So that's something that we need to discuss. And finally, regarding the last point, we need to also discuss that should our action reproduce all 4 of these Maxwell's equations as Euler-Lagrange equation, or should it reproduce some subset of it? Is the question clear? I'm asking the question that should all 4 Maxwell equations be reproduced as Euler-Lagrange equations? Okay, so let's start with the last point first. Let's start with this thing first. Anyone has any guess? Anyone wants to guess something or has an idea?
Sir, I think we derived Maxwell's equations from the canonical quantization when we took Arpitsar's class. I think we derived those from generators, from the Poincare generators. Does that make sense?
I don't think it does. You definitely cannot derive a dynamical equation just from symmetry arguments alone.
But we did derive those. I forget. I will Slack you. I will send you in Slack.
Okay. Anyway, so let me rephrase the question in slightly different manner. Are all 4 of this Maxwell's equation in same conceptual footing or not? Or is there something fundamentally different about them? this is the question that is independent of any quantum theory. You can ask this question and you should be able to answer this question even at the level of classical electromagnetism. So, okay, let me discuss this thing. So the basic point is that the crucial difference is that if you notice here, the sources for the electromagnetic field, which are the charges and the currents, they only make appearance in these two equations. Whereas these two equations, they're completely insensitive to the presence of charges and currents. So whether my theory has any free charges or currents or not, these two equations simply do not care. And that sort of gives us a hint that even in an interacting theory, these equations can already be true irrespective of what kind of charges and what kind of currents are present in my theory, or if there are at all any charges or currents present in my theory. Okay. So this makes the homogeneous Maxwell's equation a little bit different. So the answer to this question is that no, we should not try to derive all four as Euler-Lagrange equations. In fact, you shouldn't be able to do that because these two, the homogeneous Maxwell's equations, they should hold even off shell. Okay. So this will turn out to be part of an identity. It's an identically true statement.
Sir, is off-shell means here they don't follow Euler-Lagrange equation? They don't satisfy
Yeah, so,
Euler-Lagrange.
Yeah, so off-shell will mean that whether or irrespective of whether the Euler-Lagrange equation holds or not, this will be true. Does that answer your question? Okay, I hope it's clear. So let's move on. So of course, we don't want to work with Maxwell's equation in this form because it's not very convenient when you are working with something which is invariant under special relativity, but the notation doesn't make it very manifest. So we want to use four vectors, which once again, I'm assuming all of you are familiar with. So we use four vectors to make the Lorentz symmetry manifest. And so define the contravariant four vector, some A0 and A, define a four current whose zeroth component is 0, and then the special component is J. And A0 we will identify as the negative of the electrostatic potential. So this is and this A is the familiar vector potential. And we define the Maxwell field strength tensor. The contravariant one should be defined as this, and then you can define the covariant one by usual raising or lowering. And then you can easily check, for example, if I look at F0i, all downstairs, this is del 0 AI minus del I A0, which is essentially minus del TA minus del I phi. So this you can recognize as the ith component of the electric field. And similarly, if you look at Fij and multiply it with epsilon ikj, this thing will turn out to be curl of A's kth component, which is essentially identified as the magnetic field's kth component. So I'm assuming all of you have seen this before, but if in case you have not, let me give you the first exercise. That please, first is that please check that all inhomogeneous Maxwell's equation with these tensors and currents as defined takes the form del mu f mu nu is J nu. And the continuity equation that rho and the vector j satisfied now takes the form del mu j mu is 0. And finally, if we define the dual field strength tensor F mu nu, which is half epsilon mu nu rho sigma F rho sigma, then all the homogeneous Maxwell's equations, the LHS, can be written as del mu F tilde mu nu. So in particular, let's focus on the homogeneous Maxwell's equation for a bit. So once you do this exercise, you will be able to see that the left-hand side, so divergence of B, and so essentially, I'm asking you to show that this and this in 4-vector notation boils down to this. Okay? So once you have this thing, let's see that why these imply that they are identically 0. Because if I write down del mu F mu nu tilde, using the definition, this is epsilon mu nu rho sigma del mu del rho a sigma. And now this thing vanishes because see, there are two derivatives, partial derivatives with mu and rho indices. So this has to be symmetric under exchange of mu and rho. Whereas it's contracted with mu and rho that appears in the epsilon tensor, which is completely antisymmetric. So this is antisymmetric under exchange of mu and rho. This is symmetric under exchange of mu and rho. So which means that this is identically 0. So I did not need to write down. So this fact that it vanishes, it does not make use of this condition, which is why I said that it holds off shell. And this identity, in fact, has a name. It's called a Bianchi identity. Okay, so this symmetry property of under exchange of these two indices is what tells me that this is identically 0. Okay. So the lesson, what is the lesson for doing this? Remember, the first lesson is that it seems to us that the correct degrees of freedom, this should be the potentials and not the electric magnetic field, which is captured by the field strength. However, as is true for classical electromagnetism as well, the physical degrees of freedom, the ones that you observe in experiments or the ones that you can probe by experiment, is captured by F mu nu and not A mu. And this point is basically at the heart of all gauge theory, that the degrees of freedom in terms of which the action is written is A mu, but the degrees of freedom in terms of which experiments are performed or observables are performed, it's F mu nu and not A mu. Okay? So the action is represented in terms of as a functional of A mu.
But sir, F mu nu, in the expression for F mu nu, we have del A mu and then minus del A nu.
Yes, but it's not the same thing as A mu.
Ah, right. Yes, exactly. Right. Not the same thing.
So the point is that we write the action in terms of S as a function of A mu, but we have to remember that we can only observe F mu nu and not A mu directly. So it's only a specific combination of mu, which is del mu nu minus del nu mu, that you can observe, but not mu directly. This is essentially the old way of saying that potential difference is what you can measure, but not potential itself. So this suggests, so if we go back to our original checklist, we seem to have identified the correct field variables, that these guys are the correct field variables. We have also identified our answers to this, that we should try to reproduce these two as our Euler-Lagrange equations, whereas these two are something that is always true, irrespective of whether these two holds or not. And now finally, we have to answer this question, that on top of Lorentz symmetry and usual translational invariance, is there anything else, any other symmetry that we need to worry about? Well, it turns out that there is a kind of symmetry that we need to worry about, and it is tied to precisely this fact that we discussed here, because once you have this thing, you have this possibility that if there are any transformation that changes a mu but leaves f mu nu unchanged, is a symmetry of the action. I put the word symmetry in quotes for a reason. It will become clear in, let's say, 10-15 minutes. So logically, this has to be something that we have to allow, that since we are expressing the action as a functional of A, but we are claiming that all experiments are only sensitive to F, not A directly. Therefore, any transformation, if such a transformation exists, which can change A, but does not change F mu nu, has to be allowed as a symmetry of this action. Is this point clear?
So I think an example would be illustrated, like if we do a Lorentz transformation on the potential, then it won't affect the field strength, right?
Yeah, this cannot be any of the usual space-time transformations, right? Because Lorentz transformations are not a transformation that bothers us, because Lorentz transformation, we know, because both of these are very well defined objects under Lorentz transformation. One is a vector, one is a tensor. So we know precisely how they transform, and in particular, F mu nu do not remain unchanged under Lorentz transformation. It's a rank 2 tensor, so it will transform like a rank 2 tensor. So I'm looking for a transformation that will change A mu, but it will not change F mu nu. And of course, I'm going to give an example, because I would not raise this point unless it was important, right? So the example is, so that let's say that I change A mu to A mu plus some delta A mu, and this, and so let's first look at any arbitrary change. So if I just do an arbitrary change and I'm not specifying what is delta mu right now, how does F mu nu change? So F mu nu will change by some delta F mu nu, but this delta F mu nu, we know how to express in terms of delta A nu. Right? This just follows from the definition of F mu nu in terms of A mu, that if I change A by any arbitrary amount, F will change by this specific amount. Okay, so now we are looking for some kind of delta A mu such that this is identically 0. So basically, mathematically, the question is that, does there exist some kind of delta A mu such that this is always 0? And the answer is yes. If I define delta A mu to be del mu of lambda, where lambda is any scalar differentiable, so smooth function, so it's continuous and differentiable, then you see delta F mu nu is essentially del nu of lambda minus del mu of lambda. And since partial derivatives commute, this is identically 0, irrespective of what is lambda, as long as lambda is smooth function. Okay, so this transformation, therefore, has to be allowed as a possible symmetry of my theory.
But you didn't use an arbitrary del A mu. You used a specific one, but above you wrote any transformation.
So this implies this. Now the question was that can there exist some delta mu, a specific delta mu, such that this will change, be zero? For an arbitrary delta mu, clearly this is not zero, right? And we don't want that. That would simply mean that delta f is some sort of a trivial variable.
Okay.
The point was that if I change mu by some specific way, can there be some change under which mu changes, but f mu nu does not? And it turns out that there is. If a changes like this, then h will change, but f will not. And then therefore, this is something that we have to allow as a symmetry of my theory. So I have to essentially say that a mu going to a mu plus del mu of lambda has to be a symmetry. And this symmetry, it's not an ordinary kind of symmetry that you have discussed so far, because it's not parameterized by a constant parameter. Instead, it is being parameterized by a smooth function. So understand that lambda is a function of all four coordinates, x. So there is an infinitely many such transformations that are there. And these symmetries are therefore called gauge symmetry. And occasionally they're also called local symmetries. Okay, so finally we have all the ingredients in hand. We have the degrees of freedom has to be a mu. The physical degrees of freedom, however, has to be f mu nu. That tells us that on top of the usual symmetry that we expect for any relativistic theory, our theory also has to be symmetric under this kind of a transformation, which is a gauge symmetry. And finally, with these selections, we should have to reproduce only the inhomogeneous Maxwell's equations. The homogeneous Maxwell's equations are identically true as a consequence of the Bianchi identity. So that's the setup we have. Now, essentially, the idea is that to construct such an action. So we need to construct an action, SA mu, that has Lorentz invariance, because of course it has to, but it also has gauge invariance. So it's symmetric under the gauge transformation. Okay. So how do we realize that?
Anytime we change the, I'm sorry, sir. Anytime we do an arbitrary change of that field variable a mu, it's called a gauge symmetry, sir, across all?
No, an arbitrary transformation has no specific name. It's only when you change it by this, it's called a gauge symmetry. Okay. And it's called a gauge symmetry in context of Maxwell's theory. For other theories, there could be other kinds of gauge transformations. So essentially, the idea is that any transformation that affects the field variable but not the field strength is a gauge symmetry. And for Maxwell theory, it's only this transformation, which is a gauge symmetry. Only specifically this.
This is a particular form for it. Okay.
Yeah, this is a particular form. The only thing you can change here is the function lambda. As long as you choose a smooth scalar function, you're fine. But otherwise, this form is completely fixed.
Okay, thank you.
Yeah, no worries. Any other questions at this point? I don't know if people are asking questions in the chat.
I think there are 6 new comments.
So I see one relevant comment. Smoothness is necessary since we are swapping partial derivatives. Yes, I mean, but even before that, it's necessary because you are defining the transformation directly in terms of derivative of that. So it has to be differentiable, right? At least the first derivative has to exist, and in fact, more than first derivative, because you want this to be zero. So there, it has to be twice differentiable, and any twice differentiable function, partial derivatives will always commute. So smoothness, of course, you might say that it's an overkill, but I mean, we are physicists, so if we can have something which is smooth, it's even better. Okay, so let's move on. So how do we ensure Lorentz invariance? Well, that is something that you've already learned. You basically, whenever you're working with things which are vectors and tensors, you basically need to ensure that you contract all indices. And if you can do that, then essentially it guarantees that the action is a scalar, and therefore it will have Lorentz symmetry manifestly. How do we guarantee that we are working with gauge invariance? We say that in the action, the A will enter through the field strength, F mu nu. It could also potentially enter through the dual field strength, F tilde mu nu. Okay, so think in terms of F mu nu and F tilde mu nu. Of course, the action is still a functional of A, but if I can write the kinetic terms in terms of F mu nu and F tilde mu nu, since these guys were invariant, it would guarantee that the action is also gauge invariant. Okay. And then, of course, finally, we cannot forget this thing that once I have constructed this action, if I vary it to get the Euler-Lagrange equations and I set equals to 0, I should get my inhomogeneous Maxwell's equation, which was this. Okay.
Sorry, if I may ask a question. Sir, if you said the F mu nu is invariant under the gauge transformation, did we show that, or how do we know that?
This is precisely what we showed here.
The double derivative, okay.
So delta E mu, if it is like this, then delta F is 0.
So we don't concern about A mu, we just concern about the field strength and just focus, okay.
Yeah, but you're still thinking the action as a function of the A mu.
Okay.
Okay, so when you vary the action to get the Euler-Lagrange equations, you vary A mu. But I'm simply telling you that while you're trying to construct this action, if you think of the okay, look, what do you do when you try to write down kinetic terms for a scalar theory? You have phi's and you have del mu phi's, right? And then you say that, okay, fine, how do I write down kinetic term? If I have one del mu phi, I'll have to contract another del mu phi, and that will give me a perfectly scalar kinetic term. Here, you might be tempted to say that, okay, I have del mu A nu, and then I contract with another del mu A nu.
Right.
But I'm saying that if you do this thing randomly, it's not going to be gauge invariant because A changes, remember? So I'm saying that when you want to think of the derivative of A, don't just think of del mu A nu, but instead think directly in combination, which is precisely the field strength or the dual field strength. Because those guys will be gauge invariant. Okay?
Okay.
That's the philosophy. And then finally, of course, whatever action I construct, when I derive it, vary it, and get the Euler-Lagrange equations, they have to agree with the inhomogeneous Maxwell's equation, because that's what I argue. That's what it should be.
And that should give us
yeah. Sorry, go on. There was another question.
Yeah, I'm sorry. That should give us the Maxwell's equation.
Yeah, they should give us the Maxwell's equation, but I think there was someone else who was also trying to ask a question.
Sir, both Lorentz invariance and gauge invariance are symmetries of the field. So I'm asking actually what is the actual difference between them, because they both introduce us symmetries of the field. So
Okay,
why
that's
guess
not
we need why we do we need guess invariant?
okay. Good question, but there is something that's not entirely correct. Lorentz invariance is not a symmetry of the field; it's a symmetry of space-time. It's a symmetry that affects the space-time coordinates x mu. It goes to some lambda mu nu x nu, because lambda mu nu's are the generators of the Lorentz transformations, right? And then as a consequence of that, any function of space-time, whether that's a scalar function or a vector function or a tensor function, that will get appropriate transformation law. So Lorentz invariance is basically us choosing different reference frames. So I can choose one reference frame. You can choose a different reference frame which is rotated, or somebody else might choose a different reference frame which is moving at a different speed compared to both of ours, and you can have all sorts of combinations of this. Whereas gauge invariance, this is a symmetry not of space-time but directly of the fields themselves. So I'm just simply saying that mu is changing directly. It's not changing because I'm changing x mu somehow. No, mu is directly changing by del mu lambda. Nothing has been changed in the coordinate systems whatsoever. You have chosen some coordinate system, you're happy with it, you're moving on. You still have this freedom that you can still define a different potential. So this gauge invariance is simply saying that there is no unique choice of potentials. For any choice of potential, mu that you choose, I can choose a new potential, which is your potential plus any derivative of a smooth scalar function. That will be equally as good. Both of us will still describe the same physics.
Okay, thank you. I got it. So gauge invariance, actually we can transform field directly.
Yeah, it's a transformation directly at the level of fields.
Okay, thank you. Got it.
Mm-hmm. Okay. Okay, so for next 45 or 50 minutes or so, in fact, majority of this lecture, let's try to first work with the pre-Maxwell theory. We will turn on the currents later on, which means that I'm going to set J nu equals to 0 temporarily. Okay, so let's just try to get the action for the free Maxwell theory, and then we will see how to turn on the current. So that means that I want to recover as my Euler-Lagrange equation, del mu f mu nu now should be equal to 0. This should be my Euler-Lagrange equation for the action. Okay. So what do I know about any free theory? I know that they should be quadratic in first derivative of a mu of the field variable, right? Just like in scalar, it's del mu phi, del mu phi. So gauge invariance then tells us that I should think of quadratics not of arbitrary derivatives of a mu or a nu, but precisely in the combinations of f and f tildes, because these are gauge invariant. So I should look for quadratics of f mu nu and or f tilde mu nu. Right? And then finally, of course, Lorentz symmetry tells us that we should contract all the indices. There should be no free indices left over. So with that, there are not many possibilities, right? There are essentially three possibilities that I have. So I can write down a term which is f mu nu and contract it with f mu nu.
Sir, we know that the quadratic nature of the action has got to do with harmonic oscillations. Does that say anything here, sir, or is that?
Well, any free theory is essentially quadratic in nature, right?
And
So
they are all
for example,
harmonic oscillators?
I mean, harmonic oscillators, if you want to think of it in terms of that, yes, you can. But I mean, basically, you should think of as that the free equations of motion should be completely linear. So they should satisfy a wave-like equation. That's the essential point. The harmonic oscillator thing is just if you want to connect it to quantum mechanics. That's the way. And you can definitely do that for Maxwell's theory, but that might not be the best way of thinking. So for example, for fermions, you don't want to think in terms of the standard harmonic oscillator that you learned. But it's still true that they satisfy a wave-like equation.
So that's where the sinusoidals and the electromagnetic waves come in, right?
Yeah, of course. I mean, we know for sure that electromagnetic wave satisfies wave equation, right? For the free electromagnetic, free Maxwell theory, the most famous solution is the electromagnetic wave.
So when you write should be quadratic in first derivative of mu, is that the assumption you're working from?
This is, of course, you can take it as an assumption, but I mean, this is a valid assumption. I mean, because without this assumption, if you work with, so how can you violate this assumption? You can simply say that, okay, there should be no derivative, but that's bad because if there is no derivative, then there is no dynamics. And we know that Maxwell's equations have dynamics. Things change with time. So you need at least one derivative. Then you might say that why don't we have more than one derivatives? You can have 2 or 3 derivatives going on, but then that would suggest that we would need more initial conditions. That if I tell you electric and magnetic field configurations at time t, you should not be able to predict what is going to happen for the electric and magnetic field later on time. And that's not true. We know that we can specify that. The initial condition specifies everything. So that tells us that there are no other higher derivatives. So the equation of motion should be second order in derivative. So the action should be first order quadratic.
These are all based on our observations.
These are all, of course, I mean, there is some sort of phenomenological input. But if you're trying to, of course, describe a theory whose free action is like 4th power of derivative acting on something is equals to 0, then of course this is not a valid assumption. We would have to modify this. But that is definitely not true for Maxwell's theory.
Okay, sir. Okay. Thank you.
So you have this quadratic that you want to consider. So you have one option, which is f mu nu contracted, and I can integrate over that. And I can put some completely arbitrary constant in front of it because I don't know yet what number this should be. And of course, I can also do f tilde mu nu contract with f tilde mu nu, and I can integrate over this thing. This also fits the bill, and I put a different constant in front of it. And finally, I can consider a quadratic where f mu nu is contracted with f tilde mu nu. And then I integrate over it, and I put a different constant in front of it. Okay, so this is the most general ansatz that you can sort of come up with if you're trying to write down an action which satisfies all these properties. So this action is definitely Lorentz invariant, it is definitely gauge invariant, and it is definitely going to give an Euler-Lagrange equation which has the correct structure, which has at least the hope of recovering this thing. Okay.
Yes.
So now with this, I'll leave you as an exercise for you to check 2 things. And this is an important exercise. One is that starting from the definition of the f tilde, you should be able to show that f tilde mu nu full contracted. This is not a new term. This is in fact negative of f mu nu contracted with f mu nu. Okay, so this is essentially telling me that the first and the second term are basically the same. So you can just write one of them, forget about the other. The second exercise that I want to give you is the last term where you contract f mu nu with f tilde mu nu. This you should be able to show that it's proportional to del mu of epsilon mu nu rho sigma a nu del rho a sigma. So it's a total derivative, And if you impose the standard boundary conditions that fields fall off fast at infinity, so then you can ignore this because of boundary conditions.
So it's
that
0?
tells me, sorry?
It is 0?
It is 0 if you impose the standard boundary conditions, right? You have a total derivative, and then if you integrate total derivative over before x, right?
Yeah.
So this is telling me that the most general ansatz that we constructed, coupled with these two mathematical facts, simply tells me that this is pretty much the only option that we have. This is secretly same as this. So I can just simply rewrite it and absorb this constant in this constant. So I don't need to worry about this. And these do not give any contribution because it's a total derivative. So I can just use Stokes' theorem, write it as a boundary term, impose boundary condition, and this vanishes. So essentially, it's only this. Okay. And now our task is that once we have this thing, it fits all the bill, and it's pretty much the only unique candidate that we have. It better reproduce this. So we finally have our candidate that SA mu is some constant f mu nu d4 x. Now, remember, I need to think of the action as a function of A. So the time has come where we express this in terms of we express the f mu nu in terms of the derivatives of A nu following the original definition. So when you do that, you essentially get del mu A nu minus del mu A nu del mu A nu. This twice comes because I use the fact that this is also antisymmetric, this is also antisymmetric. So I can just keep one term here and multiply the two terms here, and I put a 2 here. So you can just, you should check this from this. It will just take you 2 minutes to check that. Once we have that, we can simplify this even further. I want to integrate by part this term. And when I do that, I put a minus sign. I throw away the total derivative piece. I get del square A nu. And then I integrate by part this as well. So the del mu comes here, which I can push through del nu. And the del mu A mu, I can write as del dot A. So this becomes A nu del nu of del dot A. And then, of course, thing is integrated. So here I have integrated by parts, both the term. And threw away the total derivative. For the same reason as we threw away any total derivatives. Okay. So the action is simplified like this. Now I can do the same standard thing that I vary the action with respect to A mu. And this gives me. So notice that both of them are quadratic on A mu's. And in fact, you can check that when you vary, of course, one's variation will hit this one, and then one's variation will hit this one. And similarly here, one's variation will hit this term, and then there'll be another term where the variation hits this term. Both of them will give you the same contribution. So that's why this twice becomes 4 times. And then this is del square A nu minus del nu del dot A. And of course, d4x. And now what does my Euler-Lagrange equation tell me? Euler-Lagrange equation tell me that this delta S A mu has to be 0. And the only way this will be 0 if this thing inside the square bracket, this is equals to 0. So that's how I get the equations of motion. So this means that del square A nu minus del nu del dot A is equals to 0. And if you re-express this in terms of the field strength, you can show that this is precisely del mu F mu nu is equals to 0, which is the Maxwell's equation that we were after. So now the only thing that is left is this overall constant A. Of course, there is no physics principle that can fix this constant, because given any action, I can multiply it by any other constant, and it is still an equally good action. One thing that we can do is that choose a number that will simplify our life going on forward. And it turns out that it will be really good that when I vary this action, I get this number minus 4a. If this number was just 1, it will make our life simpler going on forward, that we will not have to deal with some pesky factors. And therefore, a natural choice is to work with a minus 1/4. Mind you, this choice, there is no physics behind it, no maths behind it. It's just a matter of convenience. Okay, it just helps us. So finally, our candidate action that reproduces the free Maxwell theory, and we have argued that this is pretty much the unique action that you can write down, is this. Remember that F mu nu is defined as del mu A nu minus del mu A nu. Okay, so this action checks off all the boxes. It reproduces the free Maxwell's equation. It is Lorentz invariant. It is gauge invariant. All of this is checked off. And then this is pretty much the only thing that you can write down which will have all these properties. Okay, so are there any questions on this point on writing down the action?
Maybe I'm asking ahead of time, but you haven't mentioned why we need the gauge invariance, or talked about the gauge symmetry and local symmetry.
Sorry, what's the question again?
You haven't talked in detail why we need the gauge invariance, gauge symmetry.
Mm-hmm. Okay. Any other questions other than this?
The previous one here in the third line, you said the bracket should be 0. So why not delta A nu? This part cannot be 0. Why? Delta A nu cannot be 0. Why?
Because that's the definition of the variational problem, that we say that for arbitrary changes of delta A, this delta S should be 0. If this bothers you, maybe you are more used to seeing delta S, delta A nu, and then you don't have that delta U here. You just have this.
Oh, okay. It's arbitrary change.
Okay. Okay, so well, with this, we had a question that I have not discussed, that why we needed a gauge symmetry or gauge invariance, and that was a very coincidentally timely question, because that was precisely the thing that I'm going to discuss now, that why do we need gauge invariance in the first place? Why is it? Because this is the first time, hopefully, you are encountering a situation where the field variable in terms of which the action is written is not the variable in terms of which the experiments are being performed. So this weird split, why is it that we write the action or think of the action in terms of A mu, but we demand that what is actually going to be observed is F mu nu? Why is this weird split that is happening? And there is a very deep reason behind it. So let's discuss that. So one of the first crucial thing in trying to do any quantum field theory, in fact, in any quantum theory, even in quantum mechanics, the thing that you need to ensure at all stage is unitarity. This is essential. This is non-negotiable. You cannot do quantum theory without unitarity. So I'm told that you guys have seen a little bit of group theory and a little bit of representation theory of Lorentz group and Poincare group in particular. So all of you have studied that all particle states, they are basically going to form unitary irreducible representations of the Poincare group. Right? So depending upon how you taught it, you might have seen it like ISO 3,1, or you might have used different notation. Doesn't matter. It's the Poincare group. And you have also probably seen that states, the particle states, these are labeled by eigenvalues of the p-square operator and the Pauli-Lubinsky operator, which essentially gives you the mass and the spin or the helicity.
So do we write
So
ISO 3 or ISO 1.3, sir?
Either way is fine. Whichever, if you're used to seeing 1,3, that's fine. 3,1 is also fine.
Okay, sir.
It's just two different notations. There is no meaning to either of them.
All right, thank you.
Okay. So in my lecture, I'm going to do a slight abuse of terminology, and I'm going to use spin to mean both spin and helicity. So typically when you have massive states, you talk about spin. When you have massless states, you should talk about helicity. But I will also talk about spin of the massless states, and actually what I would mean is helicity. Okay. So that's just a disclaimer. And of course, you can have any other internal quantum numbers if there are any. But so far, we have not encountered a situation where we need any other internal quantum number. But if there are any other internal quantum numbers, you will need them as well. So with that, there is a complete classification that was done by Wigner a very long time ago. And he essentially found out that if I look into the spins, and if I look into the how many degrees of freedom those particle states are going to carry on shell, then he found that, for example, spin 0 would have degrees of freedom 1, spin 1 would have degree of freedom 3 if it's massive. It would have degrees of freedom 2 if it's massless, and so on. I'm focusing only on bosons here. Of course, fermions have their version of the story as well, but we know for sure that electromagnetic wave is captured by a boson. So now you see the classical electromagnetic wave. We know it since Maxwell's time that this is a wave which moves with the speed of light in vacuum. And special relativity tells us that if anything is moving at the speed of light, then the particle state corresponding to it has to be massless. There's no other option. And we also know that it has two independent polarizations. That tells me that whatever is the particle for this electromagnetic wave, which is what we call a photon, these photons must have m equals to 0. And from this table, it tells us that if m equals to 0 and it has two polarization, then therefore it must have spin 1. So it must have spin equals 1. And therefore, Wigner tells us that it should have only 2 degrees of freedom on shell. All of this is absolutely essential. If you negotiate with any of this, if you want to change any of these numbers, you are at risk of violating unitarity. And if you violate unitarity, you are not going to build a consistent quantum theory. Things will go wrong. Okay, so everything that I have tabulated on the left-hand side is non-negotiable. It's essential. You cannot play around with it. On the other hand, there is something else that we have when we we consider when we want to talk about field theory, we have Lorentz symmetry. And in fact, I should say manifest Lorentz symmetry. So of course, Lorentz symmetry is there, but is Lorentz symmetry manifestly there? Just looking at the action, can I immediately say that, oh, this is Lorentz invariant? Okay. This is not, in some sense, essential. You do not have to do this. So for example, Maxwell's equation, nothing goes wrong if you express it in terms of this E, B, curl of E, divergence of B, this form. You can solve for it. You can get solutions. You can live happily ever after as far as classical electromagnetism goes. But the fact that they have this symmetry, this huge, nice symmetry, Lorentz symmetry, which is not clear, not transparent when you use these variables, electric and magnetic field, is a bit of a problem when you want to do complicated computations, which you will have to do when you are pushing the theory to go beyond classical limit and talk about its quantizations and so on and so forth. So manifest Lorentz symmetry is extremely useful in doing these computations. So while this is not essential, it is very, very useful. And of course, this is not a new realization. This is a realization that has been there for more than 100 years now. And we know that if I want to capture interactions which are local, they are best captured in terms of fields. So I have some field, they can have some sort of index. But the point is that these are some local functions of the space-time. And then we also know that the best way to construct a Lorentz invariant action out of these fields is when these fields transform nicely under Lorentz transformation. So they transform like a scalar, a vector, in general, a tensor, and so on. And this is also something that mathematicians have figured out a long time ago, that if I have the rank of the tensors in 4D, and I see that how many variables or how many components does it have, then of course, if you have 0, which means that it's scalar, right? It's a scalar, something like phi x. It has only 1 degree of freedom. It's just one number at each point. If I have a vector, something like a mu x, the potentials that we are considering here, it has 4 components. So I have to specify 4 numbers at each point. And then the number goes even worse. If I have something like 2, I will need more than 4 and so on and so forth. And now you see we are at an impasse. We have a situation where the quantum mechanics is essentially telling us that photons should be captured by something which is massless and spin 1. Therefore, it should have 2 degrees of freedom. On the other hand, there is no scalar vector tensor that has only 2 components. There is something which is 1, the very next is 4, and the next one after that would be even more than 4. Okay, so we are at a situation where we definitely cannot use scalars because they are too few. And if I use vectors, then it's too many.
Matrices.
Sorry?
Matrices.
There are no matrices here.
Rank 2 matrices? Oh, okay.
Yeah, rank 2 will be a tensor, but it will have even more than 4, right? We are trying to trying to find a field variable which will have 2, exactly 2, ideally. So therefore, it tells us that there is no way you can have a manifestly Lorentz invariant description with only precisely the degrees of freedom that you need. So you will, if you want to keep manifest Lorentz symmetry, which is always a good idea when you want to do a computation, then you have to work with something which has more degrees of freedom than you need. Okay, so which is why we chose the vectors, we chose the potential.
What is rank?
Rank, okay, loosely speaking, rank means how many indices does it have?
Okay. Do you mean rank of a tensor?
Rank of a tensor, yeah.
So, but rank 2 tensor is a matrix. Can we use matrix here? No.
If you use matrix here, you are making the situation worse. I'm telling you the point is that you want to get something which has only 2. So this scalar has only 1, vector has already 4, a rank 2 tensor, and if you do not impose, if you do not tell me any symmetry, then in general it will have 16. That's even worse.
Okay, we need 2, right? Yes.
So if you need 2, your best bet is to work with AMU, which has 4. But out of this, only 2 are physical. And therefore, there should exist some symmetry, some sort of redundancy that will help us remove this extra 2 degrees of freedom. And that is the role played by gauge symmetry. That's the job of the gauge symmetry. And this is a very important point. So let me just summarize again that gauge symmetry allows us to remove the extra degrees of freedom which are unphysical while maintaining manifest Lorentz symmetry. Okay. So this is the most important reason why gauge symmetry has to be there. There is a second reason why gauge symmetry has to be there, which we will elaborate on lecture 3, but I will just mention it now, that this gauge symmetry also allows us to find the matter coupling. So we don't want to just do free Maxwell theory. We want the free Maxwell theory to interact with charged particles and charged fermions, charged other type of particles if there are any. And to do that, we need to find out the interaction terms, like what kind of interaction terms can I add to this Lagrangian? And it will turn out that gauge symmetry plays absolutely the most important, perhaps the singularly most important role in doing that. We will not discuss it now. We will see that in lecture 3. I mean, my lecture 3. Yours, I guess, should be 12. Okay. Okay. So one important lesson that you should take away from this discussion is that gauge symmetry, now I want to explain that why I wrote symmetry, the gauge symmetry within quotes earlier. Gauge symmetry is not an actual physical symmetry. It is simply needed because we are using a field variable, a degree of freedom, which is more than what we actually need. So we are choosing a description in terms of AMU. This is our choice, that I want to describe Maxwell's theory in terms of this AMU. Why do we make this choice? Because this will help us keep Lorentz symmetry manifest. But once we make this choice, this has 4 degrees of freedom, of which 2 are physical and 2 are extra. And therefore, if I want to do a theory which is consistently going to describe the correct physics, I need to have some way of getting rid of these extra things. And that's the job of gauge symmetry.
So here you say the gauge field mu has 4 degrees of freedom. Does that have any connection because it has 4 components? Like, time and 3 special?
No, it's just, it is literally because of that. I mean, if I just simply tell you that there is a variable which is a rank 1 vector in 4 space-time, I need to specify 4 numbers per point, right? I need to specify A0, A1, A2, and A3. At each point, I need to specify this 4. So that's why it's 4 degrees of freedom.
Right. And
okay,
out of those 4, 2 are redundant.
Out of those 4, because we know that when we actually go on shell, that an electromagnetic wave is perfectly described in terms of 2 polarizations. So out of these 4, 2 of those would be physical. Mind you, these 2 need not be precisely A1, A2, or A3, A3. There could be some linear combinations of these 2 which are physical and some linear combinations of these 2 which are unphysical. But out of these 4 degrees of freedom, there should be 2 combinations which is physical on shell and 2 which are extra. There are various terms that are used for this: extra, unphysical, spurious. You take your pick. But these 2 are simply not needed to describe the physics. We introduced them. And why did we introduce them? To maintain manifest Lorentz symmetry. So it's a price that you have to pay if you want to keep Lorentz symmetry manifest, that you have to work with something which has more than what you need. And therefore, to make sure that these more things do not end up spoiling the physics that we are after, we have to find a way to nicely get rid of these things. That experiments do not depend on this, our observations do not depend on this. And that job is done in a nice way by imposing this gauge symmetry. So the main lesson is this point here, once again to reiterate, that gauge symmetry is not an actual physical symmetry. It's not the symmetry in terms of Lorentz symmetry or translational symmetry or any other symmetries that you may have discussed. It's not an actual physical symmetry. It's a symmetry that we need to impose because we are choosing a description which has more degrees of freedom than we need. So we need to somehow get rid of this extra things. It's a redundancy in our description, and the manifestation of this redundancies needs to be removed. Is captured in the statement that the theory has a gauge symmetry.
And is this a general statement for gauge symmetry, like in electroweak theory, or
this is a generic statement? Yeah, this is a generic statement for sure, that gauge symmetry is never an actual physical symmetry. It is always a redundancy in the description. The only thing that will change is like these numbers.
And it's always local, and it's got to do with U1 symmetry in this case and in other cases.
Yeah, I have not even said this thing U1, because as long as we're talking about free Maxwell's theory, there is no way to justify the name U1. So the U1 name will be justified when we start introducing the matter in lecture 3. We will see that. But right now, yeah, it of course it has to be local, because if it is not local, then how do you get rid of a local function?
So
you need to get
it has
rid of
to be every point in space-time, right?
Yeah, exactly. If it is not at every point in spacetime, how to get rid of something which is defined at every point in spacetime? Remember, when we talk about this degrees of freedom, we are talking about at each point. So you have to do this counting at each point. So whatever gets rid of these things has to be parameterized by something which is a function. Otherwise, there is absolutely no hope of removing this spurious degrees of freedoms.
Okay, thank you.
Sure, no worries. Okay, so to belabor this point that the gauge symmetry is not an actual physical symmetry, there is a very short calculation that you can do to sort of convince oneself of this, is to basically try and do the Noether procedure for this gauge symmetry. So all of you have seen Noether procedure and Noether's theorems in context of scalar field theories and maybe even fermions.
Yes.
So
Yes.
This is, of course, sorry.
Yeah, we have seen them. Yes.
Yeah. So this is of course a little naive, and we will see that why it is naive. But now, nevertheless, naive doesn't mean it's wrong. This is perfectly valid thing to do, and it's worthwhile doing this exercise once. So remember, the gauge transformation was a mu going to a mu plus del mu lambda. Just to keep in mind that this is sort of, we want to look into, so in the Noether's prescription, what do? You want to look into an infinitesimal change, right? So let's just put a constant, very small constant number epsilon in front of it as a bookkeeping device. Okay. Now, clearly under this, our Maxwell action, the free Maxwell action that we wrote down, this is unchanged because it's built out of f mu nu, f mu nu. F mu nu do not change under this, so the action also doesn't change under this. Even, in fact, the whole Lagrangian doesn't change under this. This means that if I do this transformation to this Lagrangian, and I get a new Lagrangian, let's call it L prime, and I take its derivative with respect to epsilon, and I evaluate it at epsilon equals to 0, this is also 0, simply because the action has not changed at all. And from there, you can derive the usual standard Noether's current. So this will be del nu, a mu, del mu lambda, which is the delta A, and this has to be 0. And you can quickly check yourself that this, with the Lagrangian that we had written a few slides back, this is del nu f mu nu, del nu lambda is equals to 0. So Noether's prescription tells me that for this symmetry transformation, the conserved current is this. So let's call it, give it a name. Let's call it j hat mu. Okay, so j hat mu is defined as f mu nu del nu lambda. There are several things that is already weird about this current. We will see that, but let's quickly check because I don't know how fluent all of you are in this computation. So let's just quickly check that this is indeed conserved on shell as a good Noether current should be. So if I just do del mu j mu hat, right, then I will have two terms. One when del mu hits the f mu nu, and it does not bother the other term. And then the other one is essentially when del mu hits del nu of lambda. These are the two terms, right? This first term, this is my Maxwell's equation. So on shell, free action, this is 0. And the second one, these two are symmetric because these are two partial derivatives. And this one is antisymmetric. So this is also 0. So we can quickly check that this is indeed 0 on shell as it should be. So now let's come back to the point that why did I say that this is a bit weird? There are a couple of things. One is that notice that there is a current for each choice of lambda. So for any smooth function lambda you choose, J mu is a conserved current. And how many such choices do I have? How many ways I can choose a smooth function, smooth scalar function on a 4D flat spacetime?
Infinite.
Infinite. So this seems to suggest that there are infinitely many conserved currents. Now that's weird, because if you have infinitely many conserved quantities, then your theory has no freedom to do anything because it has to satisfy infinitely many conserved quantities. There are infinite quantities which are, once they're fixed, once their values are given at initial time, they cannot change. And if you have to evolve while satisfying an infinite number of constants, then you're practically not going to evolve at all. There is no dynamics. So this seems like bad news. Well, bad news comes in a pair. The second point is that if you look at it, this current specifically depends on the choice of lambda. So which lambda I have chosen, which gauge transformation I have done, which means that this current itself is not gauge invariant. Now, at this point, you can say something like this, that if this current is not gauge invariant, then we simply say that, we have discussed once and for all that all physical observables should be gauge invariant. So these currents are not physical and you can dismiss them off the hand. But something is a bit weird because we started off with an action which is gauge invariant. And this has a symmetry under this transformation. So then its conserved current, all of a sudden, if it is not gauge invariant, maybe we should just simply take a bit deeper look before we dismiss it out of the hand. So now, of course, remember that it's not the current itself which is the thing which we should be worried about. From the current, you have to construct the Neutert charge. That's the thing, that's the most important part. That's the thing that you can potentially probe with experiments and decide for yourself if really there are infinitely many gauge not invariant Neutert charges are there or not. So how do you find Neutert charge from a current? Well, you look at the 0th component at some time slice. So at some initial time t equals to t0, you look into the spatial directions. So it's d3x, not d4x. It's only the spatial part. You look into the J0 component and you integrate over it. Whatever you get is the charge, right? So just using this definition, this tells me that this is F0I del I lambda. This is at some initial time integrated over d3x. Now I'm going to write this thing as follows. I want to take this derivative and pull it on both of them. But if I do that, I get a term which is del I acting on Fi times lambda plus F0I del I acting on lambda. The second term is there. The first term is not. So I should subtract that off. So this becomes del I F0I lambda. These are all at initial. Okay. Now, this second one, this term, this is 0. This is Maxwell's equation. This is the 0th component of Maxwell's equation. Del mu F mu nu equals to 0. If you look at nu equal to 0, this is the thing. This is the Gauss law, right? Divergence of E equals to 0. And the first term, it's a total spatial derivative integrated over total space. So that we know, we can use the divergence theorem to convert it into a surface integral. So there is some surface that bounds this infinite volume, and this is lambda. And I use that F0I is basically my electric field times the normal, unit normal, integrated over a surface. But this surface sigma, this sigma is where? This sigma is at infinite distance because we were integrating over all space. So what's the surface that covers the entire space? It has to be at infinity. Okay. Now look at this integral that we have here. This is some lambda x, Ex integrated over a surface at infinity. This integral is not going to be well defined unless there are very strong conditions on this function's lambda x. For arbitrary functions lambda x, this is not going to be well defined. This is simply going to be infinite. So this integral is going to exist. This integral exists only if following is true. Either when you go to infinity, lambda x is 0, or it's some constant. So you should only look for those gauge transformations which at infinity either falls off to 0 or reaches some constant value. If it is falling off to 0, then this charge itself is 0. So we do not need to worry about those charges. So all the infinitely many gauge transformation parameters, which asymptotically dies off at infinity, all those infinitely many conserved currents are actually pretty trivial because their conserved charges are zero. So we don't need to worry about that. The ones where this is constant, you can just simply take lambda out of this. So this is some constant. So let's just put some number. Let's say some number. And this is E dot n ds. And this is what? This is precisely how much electric charge that is enclosed in the entire space. And of course, it's a free Maxwell theory, so this is zero. But even in an interacting theory, you could repeat the same computations and you would just simply encounter that this is the total electric charge that is enclosed by this, and that is conserved. But that is okay. That is anyway something that we want. So this is something that is already going to be a consequence of a actual physical symmetry, that electric charge is conserved. So this is not really giving you anything new. So all these infinitely many conserved currents are either simply telling you that there is a conserved quantity called zero. So zero is a zero charge, which is not something that we care about. Or it is simply saying that there is something called electric charge, which is conserved. And it's just repeating the same information infinite number of times. It just keeps on saying that electric charge is conserved, electric charge is conserved, electric charge is conserved. But that's okay. I mean, electric charges, of course, should be conserved. And now let me just simply point out that why did I say it's a bit naive? Because the Noether's procedure, you should only use for symmetry transformations which are global, which are not local functions. So in principle, you should not even be trying to do these things, because if you do this, you can do this. It's a valid, there is no step that is mathematically unjustified or something that goes wrong. No, it's perfectly valid. But Noether simply told us that, when she proved this first theorem, which is the famous one, she also proved the second theorem. And she told us that if you have a local symmetry, a gauge symmetry, then all the time, if you repeat this usual procedure, you're just going to get something trivial every time. What is non-trivial about local symmetries is actually the fact that it helps you get rid of some degrees of freedom. And that is not something that you see by the usual Noether's procedure. Okay. Okay. So let's discuss how to turn on the source now. So coupling to currents. And we are going to, for today, we are going to treat these currents as background, which means that these currents are going to be completely classical. So the action, I'm going to write it down first, and then we are going to see it. So this is the free thing that we already have. This is the F mu nu, F mu nu. And then you simply write A mu, J mu, and integrate over d4x. Okay, so J mu is the background current. Background means that when we vary to get Euler-Lagrange equations, we do not vary J. So what happens when I vary delta S now? So delta S free, we already know what we get. We get del mu F mu nu, and then delta A nu d4x. And here I will just simply get delta A nu, J nu. I rebuilt the dummy indices to nu so that I can take things common. And now delta S equals to 0 implies, so I can club this together, write it as del mu F mu nu minus J nu delta A nu d4x. And when I do this, it implies that del mu F mu nu minus J nu equals to 0, or del mu F mu nu should be equals to J nu, which is my Maxwell's equation, the inhomogeneous one. Okay. But once I have written this thing, there should be a natural question that you should be asking, is that I seem to have violated my own rule and told you that instead of expressing in terms of everything F, I express something directly in terms of A. And A is not gauge invariant. A changes under gauge transformation. So what happens to gauge transformation? So if we do the gauge transformation, A mu goes to A mu plus del mu lambda. Let's see how we know the first one is invariant. S free does not change under this transformation, so we don't need to worry about that. Let's just look at how this term changes under this. So this changes as, so A mu J mu d4x. This goes to A mu J mu d4x plus del mu lambda J mu d4x. Now, this is, of course, the same as before. We need to worry about this one, this extra bit. So, standard trick, integrate by parts. When you integrate this by part, throw away the total derivative. This is lambda del mu J mu d4x. And this, remember, because of the continuity equation, has to be 0.
Yeah.
So therefore, even though we have expressed in terms of A mu, by virtue of J mu satisfying the continuity equation, this is gauge invariant. Now, of course, this is not the full quantum version, because in the full quantum version, we want to build. So we want to build J mu out of matter fields. So like fermions, maybe scalars. So in our natures, there are no charged scalars, but in principle, there could be. So we want to do all of that, but we will do all of that. That's the subject of the third lecture. But for now, as long as those J mu's satisfy this continuity equation, you're guaranteed that this is gauge invariant. Okay? Okay, so at this point, I will pretty much have no more anything to say about the classical Maxwell action or the classical thing, and we will now start talking about the quantum versions of it. Today, for the rest of the time, I'm just going to discuss what's the issue. Why can't we just simply barge on forward like scalar fields and fermions and straightforwardly quantize these gauge fields? There are some issues that we'll point out, and then we'll see how to tackle them and solve them in the next lecture. But before I proceed, if there is any question pertaining to the classical action, gauge symmetry, gauge invariances, all that, this is the best time to ask. Okay, so I guess there are no questions. So let's move on ahead. So we want to quantize, and let's just once again start with the simplest thing. So quantizing free Maxwell first. Okay. So first and foremost, we were not going to discuss canonical quantization of electromagnetism, but let me just give a couple of comments on canonical quantization. So we ended up with this Lagrangian, F mu nu, F mu nu. Now, if I write it in terms of the components specifically, so I have basically these two terms, right? Now notice the time derivatives of the fields, which are A's, only comes from this. This has no time derivative because there are no zero index here. Everything is spatial. So all the derivatives are gradients. So this is the only thing which has...
Sir, I'm sorry to interrupt. So far, up to this point, what we have been doing is basically classical field theory. There was nothing quantum about it.
There was nothing quantum about it. It was just classical field theory. That's right.
So now we're moving into the quantum domain.
Yeah.
Okay. Okay. Thank you.
So this when we have this F0 AI, this is the only thing that has the time derivative. But if you notice, it only contains time derivatives of AIs. So it only contains time derivatives of the vector potential. There is no term which is time derivative of A0, simply because F is antisymmetric and it's not possible to have something which is del 0 A0. So there are no terms which are basically phi dot. That means that this Lagrangian is already telling us that there is no dynamics for the scalar potential or A0. There is no time derivative acting on this. There is no dynamics of this at all. So if you fix some values of AIs at some initial time slice, then the Gauss's law essentially fixes what A0 is, and that's it. It doesn't evolve. Okay. Another way of saying this thing is that if I look into the canonically conjugate momenta corresponding to this 0, let's call it phi 0. So this is del L del 0 A0. This is exactly 0 because there is simply no term that depends on del 0 A0. There is no term. So if I take a derivative with respect to del 0 A0, there is no term. So it has to be 0. So in field theory parlance, whenever you have a canonically conjugate momentum which is identically 0 and which is not being set to 0 by virtue of some equations of motions or something like this, which is identically 0, this is called a constraint. And this essentially implies that if you just naively construct a phase space, that you say that, okay, fine, I'll have 4 components of A and then 4 conjugate momentums of corresponding to those A's, and I will have this phase space with 8 directions, that phase space is too large because your Lagrangian or the Hamiltonian will not live on that 8-dimensional phase space. It lives in a smaller dimensional phase space than that because all this pi 0 is essentially 0, always going to be 0, and so on and so forth. So this means that the standard way of doing the canonical quantization that you have learned, that needs to be updated a bit, and it can be handled. There is something called constraint quantization, pioneered by Dirac and Bergman quite a long time back. But this is a little sort of cumbersome in some sense. But I mean, it can be done. A far simpler way, if you want to proceed with quantizing Maxwell's theory in canonical quantization, is to do what we call gauge fixing. So you make use of this gauge symmetry and choose a specific gauge, and then this gets rid of additional degrees of freedom. And then you have just the physical degrees of freedom, just the physical phase space. You can proceed with the canonical quantization as you wish. But this has the sort of disadvantage that this is not going to be manifestly Lorentz symmetric. Manifest Lorentz is not there. There is a way to do it even with manifest Lorentz symmetry. This is called Gupta-Bleuler quantization. And I suggest, I mean, you can take it as a reading assignment if you like. Just look it up and read it, because we are not going to discuss this thing, but it's something that's nice to read. So just take it as an exercise if you want. But we will prefer to quantize using path integrals, simply because all of these canonical quantization method becomes extremely difficult, if not impossible, when you go to non-abelian gauge fields or the Young-Mills fields. And there, what works best is the path integrals. And the best way to see path integrals in gauge theories, the simplest example is QED and Maxwell theory. So that's why we are going to work in path integrals for the Maxwell's theory. But it can be done in canonical ways if you want. Okay. Okay. So moving on, if I have just the free Maxwell theory, in the quantum case, there is only one thing that I need to compute. For a free theory, what is the only one thing that a quantum field theory tells you how to compute? Can anyone tell me?
The correlation function? Transition amplitude?
Yes, but all correlation functions, transition amplitude, this is something that you compute for any quantum field theory. But for a free theory, not Maxwell, just for any free theory, there is only one thing that you need to compute, and all correlation functions are known forever. What's that thing?
Commutator?
The partition function.
Somebody said partition function, but I mean something even simpler than that. Like, I mean, what determines
Propagator.
What determines the? Sorry, yeah, repeat.
Propagator.
Yeah, that's 100% correct. The propagator. That's all you need. Yeah. So for a free theory, there is absolutely nothing else to compute. There is no interactions, nothing. Particles are just freely propagating. So you just need to figure out the transition probability that the particle is here at initial time and at final time it reaches there. What's the probability amplitude? And that's given by the propagator. So how do we figure out the propagator? Okay, so this was my action. Right? And now I need to, of course, re-express this in terms of this A's, because the propagator is in between the A's. So once again, we wrote this thing before, but maybe it's worth repeating just for once. And then I integrate this thing by parts again to write it as okay. So all that I have done is that I've just simply integrated by parts of the free Maxwell's action to arrive at this form. Nothing else has been done. Now this whole thing in the square bracket, let's give it a name. This is a differential operator of second order. So let's give it a name, K mu nu. Okay, it's a tensor differential operator. It's called K mu nu. And what is the naive guess for the propagator? Whenever you have something like this, it's a quadratic in fields. There's a field times some operator times another field. The naive guess for the propagator, up to some proportionality factor, is basically just the inverse of this kind. Right? It's the inverse of the kinetic term. That's the job of the Green's function. Right? All of you have seen this thing. So for free Maxwell theory, I need to find the inverse of this K, and I'm done. That's the propagator. There is not much to be done when we are doing quantum, going to do quantum field theory of a free Maxwell theory. But here comes the problem that this K inverse does not exist. How to see that? Well, the quickest way to see that is that if I take this operator K mu nu and I act it on del mu lambda, let's see what we get. So you get eta mu nu. I'm using the definition of K mu nu up here. So this is del square del mu lambda minus del mu lambda. So the first one simply tells me del nu del square lambda, and the second one is also del nu del square lambda. It cancels, equals to 0. So what is that telling me? It tells me that del mu lambda for any lambda is an eigenvector of this operator K mu nu with eigenvalue 0. And if I have something with 0 eigenvalue, then the determinant will vanish, so I cannot invert it. Now you might think that this is a bad thing, this is a problem, But this is actually good. You need this thing. Because why is this thing the zero mode? Why is this thing an eigenvector with zero eigenvalue? Because once we write the action in this way, a nu, k mu nu, a mu, I still need to ensure that under a mu going to a mu plus del mu lambda, my action is gauge invariant. And if my action is just a, k, a, then under a going to a plus del mu lambda, I better have that k del mu lambda is identically zero. It has to be true. So you couldn't have had any other kinetic term. So we could have just simply, without doing any computation, just by based on gauge symmetry, we could have argued that you can write this thing as a mu some k times a mu such that k has to satisfy this property. So gauge symmetry demands that you have this property. So the very thing that tells us that that allows us to do things manifestly Lorentz symmetric way is also preventing us from just simply inverting the kinetic operator to get the propagator for a free theory, which is the only thing that I need for a free theory. If I had obtained this thing, I'm done. There is no computations, no more things to be done. Everything is perfectly fine. Okay, so once again, just to emphasize the flow of logic, we insisted on keeping manifest Lorentz symmetry. That necessarily dictated that we have to have something which is more degrees of freedom, and therefore I need to impose gauge symmetry and gauge invariance, blah, blah, blah. And that automatically implies that the kinetic operator is non-invertible. There is no way out. Once you choose the first thing, everything just follows. It is also instructive to write this operator in momentum space.
I'm sorry, here you're making a connection between Lorentz invariance and gauge invariance. One is related to space-time indices.
I already did that. Remember when I discussed the Y gauge symmetry, I told you that we need to work with something which has more degrees of freedom because we want to keep manifest Lorentz symmetry. If you don't want to keep manifest Lorentz symmetry, just work with the two polarizations. But then it will look like those two polarizations will be two arbitrary choices of vectors which will seem to depend on reference frames, and you will have to do very painstaking computations at each step to convince yourself that the answer is actually independent of the choice of reference frame.
So in order to do manifest Lorentz invariance, we introduced.
So in order to work with manifest Lorentz symmetry, you have to work with something which is a scalar or a vector or a tensor. And none of this have exactly the same number of components as you need to describe the correct quantum theory. So you either have too few or too many. With too few, there is no option. If you have too few, there is nothing you can do. But if you have too many, you can say that, okay, let's introduce too many, but we will introduce the extra things later. And that extra things being removed is the job of the gauge symmetry. That's what we have said here. So once we have imposed gauge symmetry, it automatically implies that my kinetic term has to have a structure such that there is a zero mode for the kinetic term, which renders it non-invertible. Okay, so it's instructive to
action is gauge invariant. So that action
of course, the action is gauge invariant. I mean, here we proved it, right? That k mu del mu lambda is zero. So it means that if I change a mu by del mu lambda, this does not change. So of course, action being gauge invariant was never under doubt because we built the action by demanding that it should be gauge invariant. So let's look into this operator in momentum space. So let me just call it, maybe put a tilde. So k mu nu as a function of momentum p, and this will be eta mu nu p squared. Remember, it was eta mu nu del squared, and there were two derivatives here. So you don't worry about the i's because they will not play the most important role. So the other, whatever kinematic factor is there, you just call it k tilde mu nu. And now what's the zero mode? The zero mode is very easily seen to be anything which is E nu. Because if you just do it here, eta mu nu p squared p nu minus p mu, then this is essentially p mu p squared minus p mu p squared, which is 0. But what is even more interesting, that if I take k tilde mu nu e and I multiply it with k tilde nu rho p. So let's see what this is. So this is eta mu nu p squared minus p mu e nu, eta nu rho p squared minus p mu p rho. If we multiply everything together, this is delta mu rho p squared whole squared minus e mu p rho p squared minus p mu p rho p squared plus e mu p rho p squared. So we can cancel one of this. And what we have is we can take a factor of p squared out. This is delta mu rho p squared minus p mu p rho. This is nothing but p squared, same operator, this. So this short calculation just shows us that k tilde, if you multiply both of them together, they're kind of behaving like a projector operator. So applying them twice is basically just applying them once. And whenever you have something like this projection, it's very hard to invert them. And by now, it should also be clear from this discussion that why is it so hard to invert? Why can't we invert these things physically? Mathematically, we have already shown that you can't invert this. It's simply because there are extra degrees of freedoms which are unphysical. So you shouldn't try to find. So if you could invert this, it would have implied that there is a propagator between all components of A. But we just argued that physically A cannot have all physical components. So some of these A's are unphysical. There should not be any quantum propagator in between them. So we have to find a way to get rid of those extra guys first, get to the things which are only the physical degrees of freedom, and then look at the propagator. And then everything will work out. Okay, so our task at hand is essentially to find a way to work with the physical degrees of freedom, but all the time we want to do so in a way which keeps the Lorentz symmetry manifest. Okay, because we introduce all of these things to make sure that we have manifest Lorentz symmetry. If now all of a sudden to quantize, we have to break manifest Lorentz symmetry, then we could have just simply started with something which is not manifestly Lorentz symmetric, forgetting about all these gauge transformations or gauge symmetry, all these complications. So we accepted the cost that we introduce gauge symmetry because we want to keep Lorentz symmetry manifest. Now we will have to deal with the consequences. But then since we have already accepted the cost that Lorentz symmetry is manifest, but we have to deal with these complications, it makes no sense to give up on Lorentz symmetry right now. So we have to find a way to do these things. And that is precisely what we are going to do in next lecture using the path integral, which is a name. It's called the Faddeev-Popov technique. Okay, so I think for today, this is a good stopping point. If there are any questions, comments, please go ahead.
So could